Good morning, all my AP Chem students. We are back here talking about acids and bases, and we are starting section 14.2 on acid strength. And some of the things that we need to talk about is why are some acid solutions with the same initial concentrations more acidic than others. And if you recall, we talked about the general reaction where if I write down this is HA, and remember this is going to be our nomenclature for recognizing that it's an acid. We know that they are aqueous, and I'm also going to dilute this even further with some water. And we know that when this happens, this hydrogen right here is going to become a proton donor. That's what makes it acidic. And so I'm going to form my hydronium ion, and I'm forming my root of my acid with the anion that I have there. Another way that you might see this, if you recall that we talked about that we are not even going to be including water in our equilibrium expression, so a lot of times your book is going to jump straight to this to simplify it even further. So if we take a look at this, we know that we have conjugate acids and conjugate bases, and they are a result of these starting materials. And so we know that this is going to be our acid, and if that is true, then this over here, my anion, is going to be my conjugate base. And here then water in this case is going to be basic, and this hydronium ion is going to be acidic, or my conjugate acid. So what does all of this mean? So if we take a look on the next screen here, we have some generalizations that we can take a look at. So strong acids will have weak conjugate bases, and strong acids, remember, they dissociate almost 100%, meaning that that hydrogen ion is dissociating to 100%. And so what this is going to say is that my equilibrium position is going to shift to the right. It has this conjugate base has a low affinity for a proton, so because this is dissociating so much, it's going to shift to the right. And then my Ka is going to be very, very large when I have a strong acid. On the other side of things, if I have a weak acid, my equilibrium position is going to shift to the left. And if I have a weak acid, I have a very strong bond. And it's not dissociating very much. Up here I have a strong acid, and that means it's dissociating very, very easily. This bond actually is very, very weak, but I have a large Ka value. Over here, my Ka is going to be very small. That's an F. All right, so the concentration of the acid solution will have an effect upon the percent ionization of the acid molecules. This is particularly true for weak acids in aqueous solutions. When you are thinking of a weak acid, you should be thinking of vinegar. Vinegar is a very weak acid. Obviously, hydrochloric and sulfuric acid are both strong acids that we've used a lot in class. So you can see high dissociation, very, very strong acids. Example, it would be HCl or H2SO4. And then over here we have a very concentrated acid, but it can have a low dissociation, and a weak acid like vinegar. Acetic acid, HC2H3O2. So again, this has very, very strong bonds. This has very weak bonds, and that's why it's able to dissociate very, very easily. And so we need to take a look at affinity for that hydrogen ion, whether it's going to make it strong or weak. So another category that we need to take a look at is that most acids are oxy acids. As you see the name oxy, you should be thinking there must be some oxygen attached. Okay, so we have a hydrogen proton is attached to an oxygen atom. Now, this right here is acetic acid, as I just wrote, monoproduct, meaning that it has one hydrogen here. Diproduct, sulfuric acid, 2. Triproduct, phosphorus acid, you can see it has 3 hydrogen here. Now, another way that your book is going to show this acetic acid, we want to do a little bit of organic here, is written like this. So again, if this is going to dissociate, when I look at this, you should recognize that I have 1 carbon with 3 hydrogens attached. So if I were to draw that molecule over here for you, you can see that the 3 hydrogens are attached to the carbon. Then I have another carbon that's shown right here, carbon to carbon bond. And off of this carbon bond right here is going to be a double bonded oxygen. And then I have this OH over here, which makes it look like an alcohol, but its functional group right here makes it a carboxylic acid, and so that's why this is actually an acidic substance. So what happens here in this weak acid, you can see that this hydrogen over here is the thing that should be breaking, and that's what's going to be ionizing. Well, this is a pretty strong bond, and when that breaks, though, that's where the bond is going to break, and this is going to be slightly negative side, this can be slightly positive side, and it's dissociating with water because we recognize that water has an affiliation of a positive side and a negative side, and so there's going to be some attractions there. Now, this bond is relatively strong because I have a weak acid. If I take something like HCl, this is a very, very weak bond right here. This is able to dissociate and attract to the oxygen and water very easily. Now, each one of these have a dissociation constant. This obviously only has one because it has one hydrogen. This would just be called a Ka. This would be called a Ka1 and a Ka2 because both of these have two hydrogens, so it's a diprotic. And you can see for triprotic, it would be Ka1 plus Ka2 plus Ka3. And what actually happens then is Ka1 is the first dissociation constant, what really affects the equation the most. It's the largest value there, so it's going to affect its equilibrium much more than the other two dissociations that are going to happen. This becomes very, very small. We are mainly going to stick to monoprotic ionization because it's a little bit easier to understand. Then we're going to take a look at oxyacids, is what this section is talking about. You can see that here I have a hydrogen attached to an oxygen, and X here meaning that I have a non-metal. So if I have large numbers of oxygen, we'll have a greater shift from electron density towards the oxygen and away from the hydrogen, results in a stronger acid. So very simply, if I have HClO4 all the way down to HClO, the chlorate, you can see that I would have O3, O2, O1. This is the strongest acid right here. It's very, very strong, and this one would be my weak acid. Now keep in mind that if it's a strong acid, the bonds are very weak, and this bond is very strong, and that's why it's not going to dissociate. So if I take a look at my strong acid here, I have my chlorine in the middle, and I have 4 oxygen associated around the outside of it, and then I have another hydrogen that's attached here. This is a hydrogen that needs to break away, and this is very easy for it to do because the chlorine is going to hold on tightly to these other 4 oxygens, and so this makes it a strong acid because this dissociates very easily. Whereas I draw the weak, you can see that I have the chlorine attached to both oxygen and hydrogen. It's not as easy to break this bond. So we have, again, because of our dissociation, we're taking a look at whether it's strong or weak. So here are our strong acids that we traditionally talk about. These 3 are the first 3 that you often will hear about: sulfuric, hydrochloric, nitric, perchloric. Sometimes AP really doesn't really do too much with either one of these. Hydrobromic and hydroiodic are often considered strong acids too. Most of the time they will tell you if that's what they want you to be understanding with that. All right, then we talked about earlier in the last podcast, I said that water can act as an acid or a base. I hope you're scratching your head a little bit like, how can it be both? Well, this is still a theory that remember we're talking about these theories of acids, how can it be both? Well, they've labeled it as amphoteric, materials that can behave as an acid or a base depending upon the situation. And you can see the different examples that we have here. You should be recognizing ammonia and water as the 2 substances we've seen a lot in here. And then we have autoionization. It's a transfer of a proton from one molecule to another of the same substance. So from here we get autoionization of water. We get another K value. Kw means dissociation constant for water. So far we've had K or Kc, which is our equilibrium constant. We've had Kp, equilibrium constant in terms of pressure. We've had Ka, our equilibrium constant in terms of acids, and now we have it for water. So as we take a look, we can see that it has a dissociation constant with the hydrogen ion and the hydroxide ion. It's important that Kw is a constant at 25 degrees Celsius, which is what we've been declaring most of our situations in all year long, no matter what the aqueous solution contains. This provides the pH scale. So we'll be talking about pH here in a few minutes. Now, amphoteric. How can something be amphoteric? Well, if we take a look, go ahead and draw these equations somewhere in your notes. We can take a look at HCl plus water, and at equilibrium, it would make my hydronium ion plus my chloride ion. And if I go ahead and bracket these together, you can see that that is donating a proton. This is taking one in. And so if that is the case, change the color here so you can see it a little bit better, that if this is the case, that this is donating, this becomes my acid, this becomes my conjugate base. My bases are proton acceptors, and so this is accepting a proton here, so this becomes its conjugate acid. Well, if I draw you another equation, you are going to see very quickly that water is amphoteric. So if I do NH3, ammonia, something that smells like Windex, and water, and it dissociates into NH4 ion, the ammonium ion, plus my hydroxide. Again, keep in mind that we're applying the same definitions. So these things are acting as a pair. This and the hydroxide ion are acting as a pair. So if we analyze in terms of proton donors and acceptors, you can see that this is accepting that hydrogen proton. And so this is going to be the base. This water is donating the hydrogen ion, so that's becoming the acid. Base is its conjugate acid. Here's my acid. This is going to be my conjugate base. Well, take a look. How can water in one equation act as a base and in the other equation as an acid? So this is amphoteric. This is a series of acids and bases and how they react. And what you're going to continue to see is we just don't really have a good way of clarifying what water is. So for now, we're going to call this amphoteric. It can behave as an acid or a base. Okay, let's see what else I want to talk about here. Again, when we talk about these K constants, Kw again is just going to be product minus reactant. And so here is our water dissociating into the hydrogen ion over the hydroxide ion. And remember, we do not put water in our equilibrium expression, so this is all we would need. So if my total is 1.0 times 10 to the minus 14th, then my concentration of each one of these should be 10 to the minus 7th, that's minus 7th, sorry, and that would be a squared value. So each one of these are found experimentally, and that's the only way that you can find them. And this also leads to as to why water was able to be an amphoteric substance. So if we go down and we try to calculate this, so we're going to calculate the hydrogen ion concentration, the hydroxide concentration at 25 degrees Celsius for this value. I know that my Kw equals my hydrogen ion concentration and my hydroxide ion concentration, and that's supposed to be 1.0 times 10 to the negative 14th. Well, if I rearrange this and I want to calculate my hydrogen ion concentration, I know that the OH is 1.0 times 10 to the minus 5th. So I simply can plug that in. I would find my hydrogen ion concentration to be, remember to use brackets so we know it's a concentration, 1.0 times 10 to the minus 9th, either brackets or this is its molarity. And so we do have the concentration of the OH, we have the concentration of the hydrogen ion. You multiply those two together and you should get back your Kw constant. And if I take a look at this, I should be able to identify that this is a greater concentration than this one. And so because the OH is at a higher concentration, then I should be able to say that I have a basic solution. Prior to that, you didn't know that until you solved for the hydrogen ion concentration and be able to look at both of these in their separate states. So basically looking at their concentrations, I can say that this is more concentrated, so I will have a basic solution. Okay, that's it for the second section. The rest of the sections will be much shorter, I promise. You have an outstanding day.